Okay, so how are we doing with the basic definition of a Laplace transform by using integrals? Thumbs up, thumbs down, sideways, what do you got? How are we doing? Laplace definition, integrals, okay? They're messy, right? Yes, these integrals are messy, they are yucky, we don't like them, we don't enjoy doing them, but this is how we can find Laplace transforms. Everybody's okay up to this point, besides the fact that these are integrals that you hate. But everybody's okay up to this point? Okay, all right. So I alluded to this yesterday, but I said it really, really fast. So let's try it again. This is like, do you remember in Calc 1 when you did derivatives by the definition with the limit and it was terrible and you hated it and you got really mad at your Calc 1 teacher? And thankfully, I don't think that was me because I don't think I had any of you for Calc 1, but it was yucky and icky. And then you got all these cool derivative rules and it was really, really nice. Yes? Remember that in Calc 1? Okay. Laplace transforms are the same idea. So we've got this horribly nasty definition with an integral at the very beginning. We're going to do it that way a little bit. And then we're going to say, no, I don't want to do it this way anymore. This is not fun. That's where the table that's in the front part of your book comes in. And that's the sheet that I popped up yesterday. So there's a bunch of examples in there, or rules, I guess. They're kind of like derivative rules. These are all your rules for calculating Laplace transforms. For example, if I pop up this sheet and I didn't have it open before class, this is also me needing to get prepared for stuff. Hold on a minute. Table of Laplace transforms. Okay. So let's share my screen here again. Okay, so here's your table of Laplace transforms, right? These are like derivative rules. So again, we did this one yesterday. The Laplace transform of 1 is 1 over s. The Laplace transform, we didn't do this yesterday, but this one you'll do in your homework. The Laplace transform of t is 1 over s squared. So these are kind of like your derivative rules. You're going to want to have these in front of you. You don't have to memorize them. I will let you use this chart for your homework. You can use this chart for your next test also. So these are not things that need to be memorized, unlike derivative rules, but I think you're going to get more familiar with them as we go on. Okay. So the one that you're going to use an awful lot is t raised to the a, and that's this function that we talked about last time called the gamma function. So let's explore the gamma function a little bit more. Again, I wrote it down yesterday, but we should evaluate it in a couple of spots, and then we'll find a Laplace transform of something to fractional power. So let's go back to the whiteboard. I'm getting better at this marginally. So remember my gamma function here. This is what I had. You don't need the definition, at least not right now. But my gamma function of, we'll do sailboats in this case. My gamma function of sailboat is equal to sailboat minus 1 times gamma of sailboat minus 1. Or if you want it with n's, gamma of n plus 1 is n times gamma of n. Those are your two basic rules for the gamma function. And the cool part is, if n is a positive integer, remember z is the part for integers and the plus means positive. If n is a positive integer, then gamma of n plus 1 is equal to n factorial. And so what that means is that gamma of n is n minus 1 factorial if you do some plugging in. So if you have a positive integer, then you can figure out the gamma function really, really easily. If you don't have a positive integer, then you have to use this recursive definition up here. So if you don't have a positive integer, then you have to use this recursive function. And the one note that you're going to want for the gamma function, the one key value, is that gamma of 1/2 is the square root of pi. That looks ridiculous, but it's correct, and you could evaluate that using the integral for the gamma function if you wanted to. I am absolutely not going to make you do that, but gamma of 1/2 is equal to the square root of pi. So let's evaluate the gamma function first, and then we're going to find the Laplace transform of something. For example, if I want to do the gamma function of 5 halves, for example. So this is not a positive integer, right? 5 halves is not a positive integer, so I can't use my factorial rules. This doesn't work, so I got to do my recursive rules. So what this is using the sailboat rule, 5 halves minus 1 times gamma of 5 halves minus 1. Think your sailboat rule right up here, right? Sailboat rule, and you get gamma of 5 halves is 5 halves minus 1 times gamma of 5 halves minus 1. So we can do a little simplifying. This is 3 halves times gamma of 3 halves, okay? And I still don't know what gamma of 3 halves is, so we got to take our recursive relation down one more step. So the 3 halves stays out in front, and then using my sailboat, this is going to be 3 halves minus 1 times gamma of 3 halves minus 1, right? It's a recursive relation, so you can subtract 1 again using your gamma function. And now I think we're in a place where we can evaluate. So 3 halves times 1/2 times gamma of 1/2. And then there's that hint that I gave you coming in. So your answer is going to be 3/4 times the square root of pi. 3/4 times the square root of pi. So that's how your gamma function evaluates. You need to get it down to fractional values. Okay? All right, so let's do a Laplace transform here. So let's talk about kind of sort of one that Seth was asking about a little bit. Let's do the Laplace transform. Actually, this isn't Seth's, but we'll do an inverse one too. Let's do the Laplace transform of t to the 5 halves. So I'm going to do the Laplace transform of e to the 5 halves, t to the 5 halves, sorry. If I want to go back and again look at my chart, a is equal to 5 halves in this case. Yes, I'm looking at t to the a. A is equal to 5 halves. That's really small. I don't even think that you can see that. Let's make this a little bit bigger. So if you have your chart, there we go. T to the a. So a is equal to 5 halves in this case. So this is going to be, if you look at your chart, you're going to want to have your chart in front of you. Looking at your chart, a is 5 halves, and I don't have my chart in front of me, and I don't have this memorized, so let's pull out my book. This is going to be gamma of 5 halves plus 1 over s to the 5 halves plus 1. All good? So far so good? Everybody good? Okay, so that means I'm going to have gamma of 7 halves over s to the 7 halves. And that means I also need to evaluate gamma of 7 halves. So I got to do recursive. This is going to be 7 halves minus 1 times gamma of 7 halves minus 1. I do my recursive formula. So 5 halves times gamma of 5 halves. And we totally did that one on the previous slide. 5 halves times 3/4 times the square root of pi. That's from my previous example. We just did that one. So we can do a little bit of multiplying, and my numerator is going to be 15/8 times the square root of pi, and then divided by s to the 7 halves. So 15/8 times the square root of pi divided by s to the 7 halves. If you put t to the 5 halves into the Laplace transform, the function you're going to get out is 15/8 times the square root of pi over s to the 7 halves. Okay, I'm going to stop sharing my screen so I can see all of your faces, and the screen share will pop up back again when we get back to the whiteboard. But how are we doing up to this point? Everybody good? Everybody okay up to this point? Doing all right? Okay, so now let's go back to the one that Seth asked, and let's go backwards, because sometimes you have to mess with the constants a little bit if you are going backwards. We'll do an easier one going backwards first, and then we'll do one where you have to mess with the constants a little bit more. So let me go back to my whiteboard here. Let's say that we want to do, for example, inverse Laplace transform of, I don't know, 5 over s cubed. inverse Laplace transform of 5 over s cubed. So let's say I want to do this one, inverse Laplace transform of 5 over s cubed. If you look at the chart in the front of your book, or if you look at the chart that's in Moodle, you can see that the inverse Laplace transform of n factorial over s to the n plus 1 is equal to t to the n. So that's one of the rules in the front of your book. Inverse Laplace transform of n factorial over s to the n plus 1 is equal to t to the n. All right, so I'm matching stuff up here. In this case, I have a 3 in the denominator, and in my rule, I have an n plus 1 in my denominator, which means that I want to use n equals 2 in this case. I'm very clear on why n equals 2 if you match up exponents in the denominator. All right, so I know that the inverse Laplace transform of 2 factorial over s to the 2 plus 1 is t squared. Or in other words, if I do a little bit of simplifying, the inverse Laplace transform of 2 over s cubed is t squared. Inverse Laplace transform of 2 over s cubed is equal to t squared. Well, that's great, but that's not quite what I have. I have a 5 in the numerator and I want a 2 in the numerator. So here's where we have to do a little bit of messing around with the constants. I am going to say this is the inverse Laplace transform of, I know what I have for the inverse Laplace transform of 2 over s cubed. I can totally do that one, that's fine. But that's not what I had in the beginning. I originally had a 5 in the top, and then I magically multiplied by a 2 in the numerator, so I have to undo that and multiply by a 2 in the denominator. So I'm rewriting to get the inverse transform of something that I am familiar with so that I can use my rules. So this is going to be that 5 halves just comes out in front, and then from what I had over on this part of the screen over here, I know that inverse transform is t squared. So my inverse Laplace transform that I'm looking for is 5 halves times t squared. We needed to mess with the constants a little bit to get the inverse transform of something that we knew. Needed to do a little bit of messing around with the constants. Okay? Here's what I'm going to do. I want you to do another one, but I'm going to put you into breakout groups for this one. So could you please do the inverse Laplace transform for me of 14 over t, or s to the 5th. This is an inverse transform, so it's going to have s's. Inverse Laplace transform of 14 over s to the 5th. That's the one that we're looking for. Inverse Laplace transform of 14 over s to the 5th. Inverse Laplace transform of 14 over s to the 5th. I'm going to stop sharing my screen. Inverse Laplace transform of 14 over s to the 5th. I'm going to put you in the same breakout rooms that you were before, so here you go. And then take just a couple minutes, work through that one and compare answers. You should get an invite to join your breakout rooms here. There you go, people are going. So go ahead and join your breakout rooms, do that one. If you didn't get the function, hopefully someone in your breakout room has it.